Over the course of many years of vibrations research here at OSU, Dr. Moretti and I have worked out methods of measuring natural frequencies of things like heat exchanger tubes, and it is a little bit more difficult than it appears on the surface, which I'll try to demonstrate here. I have a bar of steel, roughly 1 inch thick and about 15 inches long. If I could measure the natural frequency of this in bending, I could determine the coefficients from which I could determine other frequencies, etc. And quite often in the textbooks, one sees a case where beam is suspended on pinned ends or simply supported ends. Now I've put this on 2 hard rubber wedges, and this should approximate the pinned end condition. And so we'll try to excite this with a hammer, and I could measure the displacement of this with a strain gauge or a laser micrometer or something like that. We'll get the frequency. However, the bar is not cooperating. It's not vibrating, which indicates that that is not a true pinned end or a true simply supported end. Now, if I move these rubber blocks in to approximate the nodal point, however, of the bar in free vibration, if I put the rubber bars at the points of the nodes, then it is as though the bar is vibrating in space, and if I strike it, I'll get a very long-lasting signal which can easily be measured. And it seems like a trivial exercise, but some years ago we were trying to measure the frequencies and modes of some heat exchanger tubes that were corrugated, looks like intestines, and so by using this type of test we were able to determine the effective section modulus and stiffness. So it's good technique to use, and in fact this is the basis for some experiments that we've done in exp013 for many years, in which the students find the modulus elasticity of a mystery material.